Hello. I've had a request to do a video of the entire review package, and I will get through as much as I can in as short a period of time as I can. Starting now. First question. Newton's second law of motion is best shown by which of the following equations? Second law is just F net equals ma. So this is just that rearranged. Done. We got a 45 kilogram rock experiences force of gravity of 168 newtons on the surface of the moon. We want to know gravitational field strength on the surface of the moon. Now, gravitational field strength is newtons per kilogram. It's also a fancy way of saying acceleration. It's kind of two sides of the same coin. Things accelerate at 9.8 meters per second squared on Earth because the Earth pulls with a gravitational field strength of 9.8 newtons on every kilogram of mass. And so to do this, if we want to find A, we can just do F net, which would be gravity divided by m, or just newtons per kilogram. We want newtons per kilogram. We're going to take the newtons divided by kilograms. 168 divided by 45. Pretty sure that will be 3.7. All right. Next guy. We got two forces acting at a single point. If you want to add two vectors, it doesn't matter what they are, displacement, force, velocity, you got two options. You can either break everything into components, find these two up components, add them together to find the total up. Find these two horizontal components, subtract them. This one's going to be longer, so we'd end up with a net force to the right. As these cancel, they're fighting against each other, and then you just find the hypotenuse. So this guy minus this guy would give you this. This guy plus this guy added up would equal that. And then you just do Pythagoras to find this right there. Alternatively, if you are comfortable with cosine law, I just draw them tip to tail. If you want to add forces, just draw them tip to tail. So I'm just going to draw the 12 one next to the 18 one, or tip to tail with the 18 one. I'm going to draw a little horizontal line here, because I'm going to need the angle between them. By the way, if you draw them tip to tail, maybe I'll use a different color here. The line from the first tail to the last tip is your resultant, or net. So this is F net right here. Notice it looks pretty similar to what we would have gotten if we did our little components as well. Should be exactly the same, in fact. Anyway. So with the little horizontal line here, I can figure out, hey, this looks like a Z, alternate interior angles. If that's 25, this will also have to be 25. Now, I know my 12 Newton force also makes an angle of 31 relative to the horizontal. So I've just shifted it up. It's still 31 right here, leading to a total angle here of 25 plus 31, or 56 degrees. So I've got two sides. I got 18 and 12 and the angle between them, a side angle side sandwich. Anytime you're doing that, you can use big boy Pythagoras, also known as c squared equals a squared plus b squared minus 2ab cos c. So if I want to find c, this F net would be my c, the side opposite the angle I know. This is the angle I know, and either of these could be A and B, because adding or multiplying is commutative, doesn't matter which order they're in. So I'm just going to say, hey, F net is equal to 12 squared plus 18 squared minus 2 times 12 times 18 times cos of the angle between them, which happens to be 56 here. Put a little square root around the whole thing, and whatever that is your answer. I'll let you figure that out, or just check the answer key, but that's another way to do it. Moving right along, we got this sucker. Big trick with these guys, don't add forces that you don't recognize. Velocity is not a force, acceleration is not a force, all that jazz. So don't add forces you can't recognize. Personally, I can recognize gravity, because gravity is going to be acting on everything on Earth, and most things elsewhere too. And there's going to be normal force. It's against a surface, so the surface will push out of itself. It says it's going at a constant speed, which implies there is something fighting the parallel component of gravity, and that's got to be friction. There is nothing else. No secret forward force. It is D. Okay. Elevator question, just like stuff we've done before. So we want to know the normal force if she's accelerating downward at 2 meters per second. If we draw a little free body diagram on this woman in the elevator, she's got gravity down, she's got normal force up, and big minus small equals ma. I know down is the big force because she's accelerating down, so down force must be winning. So I'll do a big minus small equals ma, big being gravity, 45 times 9.8. Small being Fn, the thing I'm looking for, and that's going to equal 45 times 2. If I do that, it ends up being like 45 times 8, or anyway, I should rearrange this. So 45 times 9.8 minus 45 times 2 equals Fn. Now, if I'm doing that, it's going to be pretty close to 45 times 8. 45 times 2 is 90. 90 times 4 would give me 360, but it's a bit less than that, so it would be 350 is my normal force. All right, and remember, normal force is how heavy you feel or what scales measure. Good things to know. Next question. We've got a 15 kilogram block pushed up a 35-degree incline. Friction force of 110 exists between the block and the incline. I'm going to component diagram this because I freaking love component diagrams. They make things so much more obvious. Pulling down, I'm going to have friction because it's moving up, and friction will always oppose motion or tendency to motion. And I've also got F parallel down slope. I've got normal straight out of the slope. I've got the perpendicular component of gravity into the slope. And I've got my applied force upslope. Now, since this whole constant speed thing is mentioned, I know that my upslope forces have to cancel with my downslope forces. Actually, all my forces have to cancel, but these are the ones I'm particularly interested in because I want to solve for F. So I'm going to do that by knowing it's at constant speed, so F has to be equal to my two downslope forces added together. So I'm going to say upslope forces have to equal my down because that whole constant speed thing. And so F is my only up force, and downslope we got friction plus F parallel. Friction they just give to us, so that's nice and easy. 110. F parallel is always mg sine theta. So that's equal to 110. Sorry for the bad one. Plus 15 times 9.8, which is 147, times sine 35, which would bring us roughly like, what would it be? Like 80 something. Yeah. So 190 it is. If you're wondering why F parallel is equal to mg sine theta, here's gravity, mg, and we just want to break it into a component straight into the slope, our F perpendicular, and a component straight down. If this is 35, that has to add with this one to equal 90. So 35 plus 55 equals 90. And these two have to add to equal 90. So, because, angles of a triangle add to 180. We've used up 90, so these two have to add up to 90. So that would make this 35. Top angle is always the same as this angle. And so if I want this F parallel side, that would just be the hypotenuse times sine 35, because we want the side opposite the angle. Great. Did it freeze on me? Apologies. All right. Hopefully all is going well. Well, we will hope all is working. So we got this guy here. 35 Newton force applied at 21 degrees to the horizontal is used to pull up the mass as shown. We want to do the free body diagram. Free body diagram is just, you got your applied force, you're like 35 here. You got gravity. You got a normal force. Notice it's a little less than gravity because this plus this should equal gravity because it's not accelerating up or down. And we got some friction. I had to guess we're solving for acceleration. Yes, we are. So let's solve for acceleration here. Now, anytime you're given a force at an angle like this, you are interested in the components, not the 35 itself. So your first step, let's break it into components. I'm going to pause and do that. All right, let's do this. Our vertical component is 35 sine 21, or 12.5. Our horizontal component is 35 cos 21, or 32.7. I might call this like fx and this as fy. So, first thing, I'm going to need to solve for force of friction. To do that, I'm going to have to solve for normal force. So this is commonly a first step after you've broken it into components, your applied force into components, is to solve for normal force so you can use it to solve for friction. To do that, I'm going to use the vertical axis. I've seen no indication that this thing is accelerating either down through the ground or up into the air. So I'm going to assume that there's no acceleration along the vertical axis. So I'm going to say, hey, my up forces have to cancel with my down. And my up forces are Fn plus this 12.5 vertical component. And that's got to equal my downforce, which is 68.6. So Fn, my normal force, how hard the surface is pushing up, is just going to be 68.6 minus 12.5, or 56.1. Now I've got my normal force. I can go put it into my friction formula. Friction is always mu Fn. We got mu, how sticky the two surfaces are together, and we got Fn, how hard they're getting squished together. So we put them in. 0.15 is the rating of how sticky they are. That's not very sticky. Fn is 56.1, which is a little less than what normally 7 kilograms would shove together because we're lifting up a bit. So 0.15 times 56.1 gives us 8.4 newtons back. And then it is a fight horizontally. We've got a fight between our Fx and our Fx and our normal force. So we are going to use big minus small because we got two forces fighting and acceleration. So horizontally, big minus small equals ma. Our big is 32.7, our Fx component, or our x component of our 35. And our small force is friction, which we just solved for. And that's going to equal our mass times our acceleration. And I'm going to assume you can take it from here or just check the answer key. Yeah, that is all the physics tricks. Moving right along. Large mass collides with the small with a stationary small mass. During the collision, the forces exerted on each mass are measured. Which of the following is correct about the magnitude of the forces? I don't even need to look at them. It's going to be the same. Anytime two things push on each other, it's the same. It's the whole Newton's third law. Anytime something pushes or pulls on something else, there's an equal and opposite reaction. So both masses exert equal forces on each other during the collision. They'll have very different accelerations because they have different masses, but the forces will be the same no matter what. Newton's third law. For every action, there's an equal and opposite reaction. Next guy. Two masses are connected together by a rope and pulley on a frictionless inclined plane as shown. We got a pulley thing. I'm probably going to use the whole system because I don't know tension and I don't want to know tension. It might be a little tricky to figure out which is the bigger force, like which way it's going to go. So just because this one's smaller, but this one's at an angle. So I'm just going to calculate what they are. So I'll pause for a second, do that. All right, so we figured it out. The fight between, in this corner, we got F parallel with a bigger mass and a steep angle, leading it to be the winner with 186.5 newtons versus is opposing contender at 176.4. So we got two forces fighting. The 21 kilogram one's going to win. So we know it is a down the incline situation because bigger force is going to win. And so if we're doing whole system here, we can just do big minus small equals MA. Our big force is 186.5. Our small force is 176.4. That's bigger number, smaller number. And for mass, since I'm doing whole system here, we're talking about the net force on the mass pulley systems as a whole. We're going to use the whole mass. 21 plus 18 would be 39. And that's times the acceleration. And then, so we just got like 10.1 equals 39 times A. 10 divided by, or 10.1 divided by 39 is a little bit more than a quarter, so it would be 0.26. 0.26 down the incline. Boop. There you go. That's how you do that one. Next guy, this one's kind of a fun one. Free body diagram, free body diagram, free body diagram is kind of the key. If you're looking at this, we're just looking at the ball here. Ignore the rest of it. The ball has tension on it. Maybe I'll draw it more like that, where this is like 14 degrees. And it's got gravity. That's it. Free body diagram done. Now, if I component diagram this, because the next thing I'm supposed to figure out is the acceleration, I'm going to break this into two components. I'm going to call this like Fx and Fy. If I component diagram it, it looks like this. Fy, Fg, and then Fx. It's not accelerating up or down like as it's being accelerated at a constant rate. Like it accelerates to that position and stays at that position. So Fy has to equal mg. Fg is 3 times 9.8. 3 times 9.8 is 29.4. So this will also have to be 29.4 because up has to equal down. It's not accelerating up or down. But this guy isn't canceled at all. This is your net force. And you can solve for it because you know this guy is 29.4 to cancel out gravity, and you've got an angle. So you could just use tangent. You've got the adjacent side. You want the opposite side. So if we do, we just say, hey, our net force is equal to our x force, or x component of our tension force, which is equal to the y component, 29.4, times tan of 14. And that'll give you the net force. I don't know what this is offhand. I guess I can calculate it. .3. So we get a net force of 7.3 newtons on 3 kilograms. So acceleration is just net force divided by mass, just rearranging F net equals ma. So 7.3 divided by 3 gives us 2.4 something or other, I believe. 2.43 repeater, just for fun, meters per second squared. All right, next guy. We want to know what's going on when the cart reaches a constant velocity of 6.5 meters per second. So this is just a troll right here, because constant velocity just means there is no net force. It doesn't matter what the velocity is. So that is not a useful bit of information. Now, if you think about it, like just looking at how this works, if there is any angle here, there will be an uncanceled force. There will be a net force. So the only way to have no net force is for there to be no angle. Ta-da! There you go. Once you're at rest or at a constant velocity, it should be straight up and down. Next guy. Block shown in the diagram below remains at rest. What's the friction force acting on the block? If we component diagram this, we got F parallel downslope. We got friction upslope. We got F perpendicular into the slope, and we got normal out of the slope. Now, these are the two we're interested in because we want to find friction, and we know it's at rest. If it's at rest, that means our upslope has to equal our downslope. And we have enough information to calculate F parallel, which must be equal and opposite to friction. We got force of friction equals F parallel, because our upslope has to cancel with our down, otherwise it'd be accelerating either upslope or down, which is equal to mg sine theta, which is equal to 0.5 times 9.8 times sine of 40. And let's put it. So 4.9 sine 40. Sine 40 would probably be like 0.6-ish, I think. So I think it's 3.1. Wild guess. Yeah, 3.1. Bam, done. All right, next guy. We got another one of these funny little force and angle questions. So we will just break it into components as per usual. Though actually we just want the normal force, so we're just going to do an up equals down. We're just basically doing the first step. So our first thing we need to do is find this upward component, which would be 45 times sine 35. Which is 25.8. Now our up forces have to equal our down. Up equals down. We got two up forces. We got Fn, which is what we're looking for, plus 25.8, our upward component of our applied force, equal our gravity, which is 21 times 9.8, should be 196 plus 9.8, which would be 205.8. So we got 205.8 minus 25.8 gives us exactly 180, which is kind of fun. there you are. That's how you do it. We just want normal force, and we found it because we know it's not accelerating up or down, and we just made our up forces cancel with our down. Next guy, kind of a good question. It's a two-step problem. Right now, we want to know tension in the right-hand rope, which is going to be exactly the same as tension in the left-hand rope with the massless, frictionless pulleys we talk about in this course. Now, we don't have enough information to directly solve for tension right away. So what we are going to have to do is do our big minus small on the whole system to find acceleration, because then we could apply our big minus small on just one of these masses, either or, doesn't matter which. I might do the 2.4 just because it's on the right, just for fun. And then tension would be the big force, gravity on it would be the small force, and we'd know the acceleration, so we'd only have one unknown. So first step, using the whole system, we will find acceleration. So big minus small equals ma, because we got forces fighting and one of them winning. Big force moving the system is 5.1 times 9.8, gravity on the big mass. The small force trying to move it backwards is gravity on the small mass. And we're doing whole system here, so we got to do whole mass. 5.1 times plus 2.4 is 7.5 times A. If we do it this way, we end up with 2.7 times 9.8. I'm going to pause it. All right, so the result of all this junk was an acceleration of 3.5. So switching to the 2.4 kilogram, now that we know acceleration, we can do, again, big minus small equals ma. Big being tension, small being gravity on it, and that equals 3.5 times 2.4, which happens to be 8.4. The small force, again, was gravity on this, 2.4 times 9.8, which was 23.5, giving our tension being 23.5 plus 8.4, or 31.9, which rounds to 32. Done. And the next guy. We've got something being pulled at a constant speed, so all our forces have to cancel. We want to find the coefficient of friction. We know it's being pulled forward by a 12 Newton force, which means since it's going at constant speed, the backward force must be exactly the same. So force of friction must also equal 12 newtons. Otherwise, it would be accelerating in one direction or the other. Now, coefficient of friction, our only formula involving that is force of friction equals mu Fn. Fn is going to be equal and opposite to gravity here. mg equals 5 times 9.8, or 49. So our normal force has to be 49 as well, just because there's no other up or down forces, and it's not accelerating up or down. So up has to cancel with down. So we got 12 newtons equals mu times 49. 12 divided by 49 is roughly a quarter. It is slightly less than a quarter, leaving our answer at 0.24. The next question. Two masses are connected by a light string passing across a frictionless pulley as shown in the diagram below. Free body diagram, forces on mass M1 here. We got tension, gravity, normal force, and we got friction, which is less than tension because it's going to accelerate forward. And we're probably looking for we're looking for tension in the connecting string. Never mind. So we'll probably have to solve for acceleration first, because we pretty much have to do a big minus small equals ma. We don't know tension, we don't know acceleration, but if we do whole system, we do not need to know tension. So this is a fight between gravity on this guy, 0.8 times 9.8, or what would that be? That would be 78 or 7.84. 7.84. And so it's a fight between that and friction right here. Friction, of course, being equal to mu Fn. Fn being equal and opposite to gravity on this guy. 1.5 mg is equal to 1.5 times 9.8, or 14.7. So normal force also has to be 14.7, and we got 0.35 there. So that's equal to 0.35 times 14.7. I'm going to round a little. This will be approximately 5 newtons. So we got a fight between 5 newtons and 7.84 newtons. So our whole system, big minus small, equals MA. Big is the 7.84. Our small is our 5 or so, approximately 5. Our mass is going to be mass of the whole system because we're talking whole system here. 1.5 times 0.8 is 2.3 times the acceleration. So we got 2.84 equals 2.3 times A. Gives us about an acceleration of about 1.23, roughly. Keep in mind I did round there. So then we want tension. We can apply it to either or. Maybe I'll apply it to this guy just for fun because I'm rounding it to 5. So I've got, I'm going to do big minus small equals MA on the 1.5 kilogram mass. Big is tension, which is what I'm looking for. Small is the 5 newtons, and I'm going to say that's equal to the mass of just this guy because we're just looking at that, 1.5. And I'm just going to say the acceleration is 1.2. 2 sig figs is plenty given my accuracy here. So that would be 1.8. Tension minus 5 equals 1.8. 5 plus 1.8 gives us 6.8 or so, given rounding. All right, so that's how you do that one. I'm running out of time here because I got to go to advisory shortly, but we'll see what we can get done in the time I've left. So we got a block going through here. We just want to free body diagram it. It's a rough surface, so there's going to be some friction. I think we got some normal. We got some gravity. We got some applied or rope or whatever. And we got some friction. Sounds good. Nice and easy. We want to know normal force on this block below. Normal force is just going to be equal and opposite to our F perpendicular. So we'll draw our little mg here, which is equal to 2.5 times 9.8. 2.5 times 9.8 is 24.5. And this angle is going to be the same as this angle, so it's 25. So all we need to do is 24.5 times sine of 25. Oh, sorry, my bad. Sorry, we are not looking for F parallel, which we usually are. We are looking for F perpendicular, which is adjacent to the angle. So it'd be 24.5 cos 25. Which would leave it probably at 22, wild guess. Moving right along. We got this guy here. We've got a force at an angle. We are going to want to find some components here. I will pause it briefly and find those components. All right, so we did our first step. We found a vertical component. That, remember, in this case, this is more like a lawnmower, so you're pushing down. So it's got a downward component and a to the right component. If we free body diagram this, just showing the forces, it would look like this with our applied force. We still got gravity, which I should probably make longer, but whatever. And then we got our normal force, which has to cancel both gravity and our downward component. We got some friction, and that's about it. So something like that. We're probably looking for acceleration. Yes, we are. So yeah, it'd probably be helpful to know friction, because we'd want to do kind of our forward force minus friction equals ma. But to find friction, we need to find normal force. So why don't we find normal force? Normal force is, we can figure out by saying, hey, our up forces have to cancel with our down. Because it's not crashing through the ground or flying off into the air faster and faster. So our up force is just Fn. That is our only up force. And our down forces is kind of our y component of the 65, or the 27.4, plus gravity. Gravity is mg, which is 5 times 9.8, or 49. So our normal force has to be 27.4 plus 49, or 76.4 newtons. So we've got our normal force here. We can apply it to our friction force formula, which is our step 2. Force of friction is equal to mu Fn. Mu is given to us, it's 0.25. And Fn is just 76.4. And that actually divides by 4 pretty nicely. So that would be 19.1, I believe, is our force of friction. And then we can just fight out our forces. We got horizontally, we got our x component of our 65, which is our big force, versus friction equals ma. So our big force is 58.9, our x component to our 65. Our small force we just calculated is 19.1. That's going to equal our mass, which is 5 times A. 58.9 minus 19.1 gives us 39.8 equals 5A. So it's basically 8 meters per second squared. It's pretty quick. Pretty quick. So we got a block moving at constant speed. If someone's moving at constant speed, what's the acceleration? This means the acceleration has to equal 0. F net just equals ma. Anytime you get constant speed, all your forces have to cancel. You have a net force of 0 newtons. Do this one super fast and then sprint to advisory, and that might be what you get. So we want to apply our formulas. We're looking for the tension right here connecting these two. This is kind of like some sort of forward force on it, which we don't care about or know. It's frictionless, and we also have this thing here. So we could apply our formulas to just the locomotive, which would have a big minus small, but we don't know the forward force and we don't know the small force. We could do whole system, which would just be an F net equals ma. It would just be forward equals total mass times A, which is solve for forward force, but we don't really want that. Or, better option, why don't we just apply our formulas to just this guy? It's got no friction, so the forward force on it, or the net force, is just the thing we're looking for, the tension in the coupling. So if that's the net force, it's just equal to its mass times acceleration. So F net equals F coupling for just this guy, the car. And that's equal to its mass times acceleration, which is equal to 10,000 times 0.5. Half of 10,000 is 5,000, and we are done. Maybe I'll just do this really fast. So If we want to find the normal force, up equals down. We find this component, 75 times sine 20 equals Fy. And our up force is equal to Fn plus Fy, which is whatever this is equal to. And that's got equal gravity, which is 5 times 9.8, or 49. So we got 49 equals, if I had to guess, probably like 30-ish. I don't know it close enough. Whatever. It's 25.7. So 49 minus 25.7, or about 26, gives you 23. Yes. And that's your answer. Didn't quite get through it all, but hopefully this was helpful to you. Very quickly for this one, because I like this one. Hey, your acceleration is straight horizontal. That tells you that your vertical components have to cancel. That is the only way you get a straight horizontal acceleration. So 100 sine 50 to get this component would equal 50. If we got a total down force of 50, we need a total up force of 50. And then if we wanted to find F would just equal 50 divided by sine 40 to go from the opposite to the hypotenuse. If you rearrange that, that's how you do it. All right. Thanks for listening. Hopefully this is helpful. 42 minutes. Be surprised if anyone gets this far, but yeah, thanks for listening.